Hello, I am Sri Prakash Tiwari, and currently I am working as postdoctoral fellow in Professor Bernard Kipling's research group. And I am working on organic field effect transistors, basically fabricating them and studying the performance and stability issues in those devices. So what I'll talk about today is fabrication of top source drain organic field effect transistors. So let me explain about organic field effect transistor device structure, which is we have top contact and we have bottom gate. The bottom layer is heavily doped N plus silicon, which acts as a gate. The first layer which is deposited on the bottom is gate contact, which is a titanium gold layer, 2 nanometer or 5 nanometer titanium and 100 nanometer are gold on the bottom. In between you see a gate dielectric layer, which is essentially a silicon dioxide layer, preferably 200 nanometer thick in this case. We passivate the silicon dioxide layer with a surface treatment or buffer layer, which is OTS, which is octadecyl trichlorosilane, or for N-channel transistors we have various polymer layers like benzocyclobutene or polystyrene. So we passivate the dielectric layer to prevent any hydroxyl groups to come on the surface and degrade the performance. This structure shows a semiconductor layer which is widely known, pentacene, which is vacuum evaporated, but this layer could be any spin-coated polymer which can act as a semiconductor. So here I show the actual device which has been fabricated. So you could see two parallel electrodes which act as source and drain, and there are various channel lengths ranging from 200 micron up to 25 micron, which is spacing between two electrodes. And we have some capacitor structures which are circular structures with varying area which are used to characterize the capacitance density. So to fabricate them, basically we have silicon substrates which are heavily doped and one side polished and bottom side is rough. To make the devices we need gate electrodes. So heavily doped silicon gate electrodes, but to connect the gate electrodes you need some conducting metal like gold, and hence we deposit gold electrodes on the bottom. So to do this we need to protect the front side with a photoresist. You could see the color on this wafer. So basically we protect the front surface to protect the silicon dioxide which acts as gate dielectric, and then back side we remove silicon dioxide and put a titanium gold layer, and titanium acts as a adhesion layer for this gold. So here I explained how we start with the substrate. We cut it down. Either we can dice it in a properly nice manner, 1 inch by 1 inch, or if you just need small substrates you can break it like in pieces. So these are the substrates having gold in the bottom and photoresist on the top. So this is a nitrogen glove box, and these organic semiconductors are very sensitive to moisture and oxygen. So that's why we have control environment in these boxes, where we control O2 and H2O up to 0.1 ppm level. So basically we have the substrates ready and we transfer these substrates inside these glove boxes, and then before spin coating basically we need to have the semiconductor in control ambient so that they don't degrade and we have better devices. So let's go and see how we start the spin coating process. And these boxes are basically, the pressure inside the boxes is higher than what is outside. So that's why the arm kind of things where you put your arms, they are always outside. So this higher pressure inside helps the oxygen not to go inside while we are doing the process. There is a button which helps us to reduce the pressure inside. So while I'll be putting my hands inside, I need to press that button. So for some time the pressure inside becomes low and I can put my hands inside the glove box. Before processing some solutions, we have some gloves inside. We need to protect these rubber gloves with proper gloves which are more chemical resistant. So now coming to the spin coating of organic semiconductors. So basically we have the semiconductor material dissolved in a solvent. In this case we have chlorobenzene solvent for PCBM C60, which is commonly known electron transport material. So we dissolve this material and we stir it overnight to make a uniformly dissolved solution. we can change this chuck which is used for spin coating. We have some different sizes, and this chuck should be able to hold the substrate by vacuum. So to start, I will have a substrate which is silicon dioxide with a buffer layer of a polymer BCB, and then I will place this substrate in the middle of that chuck. And the next thing I'll do is take some solution in a syringe from this bottle, and after that I'll use a filter which is in this case 0.2 micron filter, so that I get a nice and clean and uniform film on this substrate. Then I put some solution in the middle of the substrate, and the solution should be enough to cover the substrate entirely. So basically right now we are spin coating this semiconductor at 1000 RPM for 60 seconds, and the speed and time depends on what kind of thicknesses you want. So in this case we have around 80 to 90 nanometer of PCBM, but generally we can change the speed to get thicker films or thinner films. So now we have a nice film on this. You could see slightly blue color of the PCBM film on this substrate. And the next thing will be to place these substrates for metal deposition. So we'll transfer these substrates through our antechamber to the next nitrogen glow box. After we have finished the spin coating procedure, we have to transfer the samples to next glove box. So this is the chamber where we put the substrates from the other side, and then we transfer these substrates, and then we close back this transfer chamber. We have some mask holders where we put our mask, which is used for top, source, drain electrode depositions. The first one is mask for transistors. So on one mask we can do 9 different substrates. So this is the metal film. We have openings where the metal goes through in the evaporation system and it gets deposited on the substrate. I'll put this metal mask on a substrate mask holder. We have to match these metal clips properly. And we can take our substrates and tape it from the back side. So your semiconductor, it comes on the bottom, and from this side you deposit the metal. Once you have these substrates pasted on this mask, you can transfer it to a evaporation system which is attached to this glove box, so that we don't expose these substrates to the air again. So the next process would be metal deposition. After the fabrication of the devices, we have to transfer the devices in another glove box where we characterize the devices. We have a nitrogen cylinder which is airtight, and we keep the devices inside nitrogen ambient so it is not exposed to air. So this is a fabricated device what we have transferred. This is a chuck where we have a metal plate on the bottom, and in the device we had gold gate electrode on the bottom which is placed on the chuck. Now we have 2 probes for source and drain. The movement of this probe is controlled by 3 knobs. So one knob moves the probe in upwards or downwards motion, and then you have one knob on the back where you can move in a forward or backward direction, and one knob which can move it left or right. You can also move the chuck to make it centralized while you move your probes, and then you can probe these electrodes one by one. So we can actually pattern these devices to have less parasitic leakages. We can scratch the device in a way where that semiconductor area is disconnected from anything else. We can just use one probe to basically pattern the semiconductor. We can just go all around a device and cut through the semiconductor. Gently we need to touch these electrodes. We don't need to push it very hard. Check number 1 is contacting to the gate which is in the bottom of these substrates, and then you can touch the 2 probes to the source and drain. This transistor has 3 terminals. 2 are source and drain electrodes, and 1 is gate electrode which actually controls the device to turn on and off. Now we are going to characterize the devices. So transistor has 3 electrodes: gate, source and drain. And the 2 characteristics which we are interested in, first is transfer characteristics, where we scan the gate voltage from negative to positive voltage, and a current flows from source to drain electrode, and we record that current. And then at certain point you can see the transistor is switching on, which is kind of turn on voltage. So in this case it is around slightly higher than 1 volt, and then after certain time you could see the current going towards saturation region. We take a square root of the drain current, and then we could find out what is our threshold voltage. So we could take a slope of this curve, and wherever it intersects the x-axis, that voltage is called threshold voltage. And with this slope we can calculate the electron or hole mobility. The next one is where we fix the gate voltage and then scan the voltage difference between source and drain, and that is called output characteristics. I'll explain what is output characteristic. On the x-axis you see drain voltage, and at various gate voltages you have different curves, like from 0 to 4, 8 and 10. So the transistor starts, so this is scanning at 0 gate volt, and 0 gate volt means device is off, and you could see that current. As the voltage increases to the device is slightly on, and then after threshold voltage you could see the current increasing, but after certain time there is a saturation, and that's what we need in these transistor devices. Now I'll show how the transfer characteristics is done. Like device is off in certain region where gate voltage is 0 or low or in negative side. When you apply positive gate voltage, the device is on, and again when you characterize at a certain drain voltage, you could see the device turning on from a off state, and you could see that going through and coming back. This is to find out hysteresis in the devices, and these devices don't show any hysteresis, but if you have some dielectric, you could actually see a gap in going and coming down. These both scans have a kind of distance, and that is called hysteresis.